Welcome to the lesson on Lean Robotics Operate Phase. In this lesson, we will focus on the operate phase in the Lean process. Upon completion of this lesson, learners will be able to explain the concept of the operate phase and the expectations for this phase. Learners will also be able to describe the key characteristics of the operate phase and list the steps to ensure success in this phase. Let us start by defining the operate phase of Lean robotics implementation. The operate phase is when the robotic systems are fully implemented into the production workflow. This phase is important because it represents the transition from design and testing to full-scale operation, where value is continuously added to the manufacturing process. This phase also represents the end of the goal of deployment. During this phase, organizations start to see the tangible benefits of their automation investments as value is actively being generated through operational processes. The established cycle of operations provides an understanding of workflow patterns, allowing teams to rely on consistent performance metrics. With the robot cell fully completed, there are opportunities for optimization and fine-tuning to improve efficiency. Most importantly, this phase validates that the initial hard work put into planning, development, and implementation begins to yield measurable returns, demonstrating the successful transition from setup to productive operation. Let's look at some key characteristics of the operate phase. They include value addition, cycle operation, optimization for continuous improvement, and outcome-oriented. In the value addition phase, there is quality improvement whereby robotic cells ensure precise assembly, especially in tasks like battery module assembly, welding, or intricate wiring, areas where errors could lead to significant safety risks. Robots in EV production often reduce cycle times for repetitive tasks, such as spot welding car frames or assembling battery packs. The cycle operation phase has known and predictable cycles. In this phase, the robotic cell operates within a well-defined process cycle. For example, the sequence for placing and connecting pouch cells in a battery pack becomes a repeatable and measurable process. There is real-time monitoring, whereby data collected during operation, for example, assembly speed, error rates, and downtime, can be used to ensure consistent output. In the optimization for continuous improvement phase after deployment, minor adjustments, like fine-tuning gripping mechanisms or adjusting welding angles, can significantly improve production speed and quality. Robotic systems can integrate advanced sensors to monitor temperature, pressure, or alignment during the production of sensitive components like EV batteries. In the outcome-oriented phase, robots must perform tasks as well as, or better than, human workers, especially in areas demanding precision, like electrode stacking and battery cells. Critical key performance indicators such as throughput, uptime, defect rates, and utilization become essential benchmarks in this phase. Now, let's look at the steps to ensure success in the operate phase. They include system validation and testing, operator testing, integration with lean processes and feedback loops. In Step 1, system validation and testing, before full deployment, the robotic cell undergoes rigorous testing to ensure it meets production requirements, such as assembling battery modules to exact tolerances. For example, testing can simulate scenarios to validate how robots respond to minor disruptions, like component misalignment. In Step 2, operator training, technicians and operators need training to understand the interface and troubleshooting procedures of the robotic system. In EV manufacturing, this involves training on calibrating robotic arms for battery placements or replacing worn-out end effectors. In Step 3, integration with lean processes, robotic cells must align with lean principles to minimize waste and maximize efficiency. For example, avoid overproduction by programming robots to produce components just in time and reduce material handling by placing robots closer to assembly points. In Step 4, feedback loops, data from the operate phase feeds back into the system to identify potential bottlenecks or inefficiencies. For example, a robotic system assembling battery packs may highlight a bottleneck in cooling plate placement, prompting further optimization. So, why does the operate phase matter in EV manufacturing? In the EV industry, production demands are intense. Robots in the operate phase ensure scalability, consistency, and sustainability. Scalability is achieved by meeting growing demand without compromising quality. Consistency is achieved by producing identical parts with minimal variation, which is crucial for battery performance. As robots can optimize energy use, sustainability is achieved by contributing to the eco-friendly mission of EVs. In summary, the operate phase represents a critical transition point where robotic systems move from testing into full-scale operational deployment. This phase is characterized by four key elements: value addition through precise manufacturing processes, established cycle operations, ongoing optimization for continuous improvement, and a clear focus on measurable outcomes. To ensure success during this phase, organizations must implement several steps, including system validation and testing, operator training programs, and integration with lean processes and feedback loops. Through proper execution of these steps, the operate phase ultimately delivers three essential benefits: scalability of operations, consistency in production quality, and long-term sustainability of the automated processes. This systematic approach ensures that robotic automation investments translate into tangible operational improvements and sustainable business value. Thank you.